Okay, now it's 6:10, so I think we'll get started. Good evening, everyone. My name is Judah Richardson. Welcome very much to this presentation of the IEEE Iowa-Illinois Section Power Engineering Society. I am the chair of the IEEE Iowa-Illinois Section. Just some bookkeeping before we get started. If you want to attend more meetings like this in the future, check us out on social media. The section that is hosting this presentation is the Iowa-Illinois Section. You can find us at facebook.com/iowa.illinois.IEEE. Really easy to remember, just 3 words. Also, a big thank you to the Region 4, that's the Upper Midwest region of the IEEE that did their best to promote this event for us. You can find them at r4.IEEE on Facebook, and then also at company/IEEER4 on LinkedIn, and then also at IEEER4 on Twitter. You can find me myself. I'm the section chair of the Iowa-Illinois section. LinkedIn.com /in/Judah Richardson, just first and last name. And then Jose Villarreal, who is our Power Engineering Society chair. You can find him same domain as before at Jose-I-Villarreal. This is not the only event we have. We have regular events scheduled throughout the year. We have 2 monthly events every month. They're both socials. The first one of those is called Power Hour. It's on the first Wednesday of every month at 6 p.m. U.S. Central Time. It's at the same link that this meeting is currently being held at. Power Hour is actually pretty interesting because that's actually how we met the speaker that it will be presenting today. So it's a really nice way to hang out with technically minded people in a very social setting. If you would like to actually meet up in person, we do that every third Friday at 5:30 p.m. U.S. Central Time at Tangled Wood in Bettendorf, Iowa. The address there is on the screen, 3636 Tanglewood Road, Bettendorf, Iowa, zip code 52722. And that meeting actually revolves around cybersecurity. It's called Cyber Social, and it's run by the Computer Society. On an annual basis, our biggest event is CornCon. That's our cybersecurity conference. It will be in its 8th year next year in 2022. This year with its 7th year, and it took place at the Waterfront Convention Center in Bettendorf, Iowa. The date for the 8th year next year has not yet been decided, but what you do need to know that is that it is annually in the fall, usually around September or early October. The website for that is corncon.net, and then you can follow them also on Facebook at QC CornCon and also at Instagram at CornCon Cyber. Now to introduce our speaker. Our speaker this evening is Mauro Gonzalez. He's the Director of Energy Planning at Termobarranquilla, which is a part of TEBSA. Termobarranquilla is the largest thermal power generator in Colombia. Mr. Gonzalez has his Bachelor of Science in Electrical and Electronics Engineering and also 2 Master of Science degrees, one in Electrical and Electronics Engineering and the other in Energy Management and Systems Technology. The second person who did this research along with Mauro is not able to attend this evening, but I will introduce her also. She's a professor at Graz University of Technology in Austria, where she's also the head of the Institute of Electricity and the head of the Institute of Electricity Economics and Energy Innovation. And so with that, I will hand it off to Mauro to present his information to us. Go ahead and start sharing, Mauro.
Okay. Let me know if you can see my screen right now.
Yes, we can see your screen. Go ahead.
Okay, thank you. Well, first of all, I want to thank you, Judah and Jose, for giving me this opportunity to share part of the knowledge that we have learned during the development of this work. It's important to clarify that we are a mechanical engineers. So this view of the combined cycle unit is our humble view about this topic. Uh, well, we are going to present here is the basic knowledge and the rule that we need to know about the operation of combined cycle unit. And I also going to talk about the Colombia energy market because we need to have the context where we are right now. So I hope you enjoy this presentation. Uh, the agenda that we're gonna see in these presentations are a small introduction about the word. What is a combined cycle unit? This is a basic Colombian. I'm going to talk about the Colombian energy market, about thermal power constraints, combined cycle gas turbine operational constraint. This is the most important uh, part of the work. I'm going to talk about the problem descriptions, cases studies, and conclusion recommendations and future work. Okay, I have to start this presentation talking about combined cycle units are one of the most common power technology in the world due to the high efficiency and the high level of flexibility that these plants can bring to a power system. So it turns that these plants make the right complement with the renewable energy resources within the transition that we are having right now in the world. So most part of the country in the world are applying this right now. And I mean, I'm talking about the energy transition and the right complement of the energy transition of the renewable energy resource. We know that is technology there, that natural gas thermal plant. So it's important to represent these plants correctly, in the correct way, in the unit commitment problem, in order to take advantage of the flexibility and the good performance of the combined cycle unit. Because these elements are if these elements are well represented in the mathematical model, the final result could be that we are looking at this picture. So while we're looking at these pictures, we are looking at erosion on blades because of the condensation of steam water. Imagine, like, for example, when you have a good representation of these elements in the unit commitment problem, imagine that this problem, this water condensation, would be like a bullet shot into the blade that have a 3,600 RPM spinning velocity. So this can cause this kind of damage that we are looking at this picture. To simulate the combined cycle gas turbine the correct way to avoid these equipment failures, we have developed a self-unit commitment model, an optimization model, where the input of the model are the desired dispatch or what you want to simulate. And the output are the possible dispatch that the CCGT can do, taking into account the technical operational constraints of the plant, such as the minimum heat requirement for the steam or the minimum number of gas turbines to dispatch as steam turbine. I'm going to talk more about that in the next slide. So, talking about what is a combined cycle plant, the output is, I mean, this is it's not a new technology. And what we have to say about this technology is that it's the coupling of two different cycles, the Rankine cycle and the Brayton cycle, or in other words, the steam turbine cycle and the gas turbine cycle. So the output of the steam from the output of the turbine, of the steam turbine from the steam turbine, is still having is the result of the steam produced or generated by the gas turbine. So we are looking here, for example, one turbine, a combined cycle unit of one natural gas turbine and one steam turbine, one steam turbine. Sorry. So with the gas turbine, we're going to produce a steam that still have good thermal properties, and we pass this steam through a heat recovery steam generator or each RCG element, as we know as in under the territory. Then the steam is used in the steam turbine to generate more power. So this configuration allows a very efficient use of the fuel. Okay, now I'm going to talk about another concept that is the dispatch method. I mean, why we do a dispatch method? Well, we do the dispatch method, or we do a dispatch or economic dispatch, because we need to optimize three basic energy industry functions. or three basic energy industry requirements. The instantaneous equilibrium between the supply and the demand, and this is related with the frequency, the network congestion management, and the short-term electricity spread. I mean, these three basic energy industry systems become an output of the dispatch in a spot market. So we have two options to do this. We can do a decentralized dispatch or bilateral model, like we have a lot in Europe, this kind of dispatch, or a centralized dispatch or pool model. And in this kind of centralized dispatch, we have two options, a tight pool or loose pool. A tight pool is a dispatch based on cost, where the ISO decides which plant is going to generate for the next day. And in the loose pool, it's a dispatch based on prices or bids, where the owner of the generation make a bid. Colombia is the only country in South America that have a loose pool market. I mean, the other markets in South America are tight pool. So this makes Colombia a very interesting market to study, because the owner of the generator of the plant decide what to do through the bid. So if you don't want to generate the next day because you don't have the principal, the main resource, because you don't have fuel, you can bid a high price to not get into the order of the main order of the dispatch. Okay. I'm gonna in this slide I'm gonna talk more about the energy mix in Colombia. So the energy mix in Colombia is based in a hydrothermal generation, so 70% hydro, 30% thermal. So this makes Colombia an energy system vulnerable to the extreme weather events like El Niño phenomenon or low influx or extreme dry season, right? So when we have an El Niño phenomenon, we experiment here a very high dry season, and at this moment is where the system gets very vulnerable because the problem in Colombia is not the power, it's the energy. If we don't have enough energy in the reservoirs of our hydro plant, this ISO is going to suffer a lot during the operation in real time because you need that energy available in the reservoir to meet the demand. Okay. Right now, the installed capacity is like 17 gigawatts, but next year, the limit will change with the integration of the renewable energy resource, solar and wind. About 10% of the energy needs are going to come from viable energy resource, plus 70% of hydro. This means that right now our system has a lot of uncertainty due to the influx of the hydrology, and we are going to add more uncertainty with the renewable energy. So with this future and taking into account what is happening around the world with these changes in the energy sector, with the energy transition that we are having right now, and the energy crisis that, for example, Europe, China is having right now, it's possible to conclude that we'll still need dispatchable resources, like thermal power plants. And of course, all the supply adequacy or expansion of the generation could be not possible if the grid doesn't increase the transportation capacity or the interconnection between zones or areas. This is not an easy task in Colombia, but I think that government tries so hard to put in work the plans of the transmission experts in the country to enable all these new entry plans and resources that is going to get into the system in the future. Okay, in these slides, I'm explaining the process of the spot market of the dispatch. What we have first here is that all the generators, all the owners, all the utility companies, and the demand have to report to declare the the state of the availability of the facility that they have. For example, in our company, in TEBSA, we have to report to the ISO of the day the availability of the amount of energy that we are able to bring or to generate for each hour of the next day for the day ahead market. And we have to bid a price for that energy. So the ISO have to receive all that input for all the companies in the system or in the market, and he solves a unit commitment problem. Then the result of that unit commitment problem is a plan, it's a dispatch, that generation that has a commitment to deliver amount of energy for each hour for the day or for the operation day. So in the operation day, the ISO can readjust the dispatch to guarantee availability. This is an example of the unit commitment that we have all the day here in Colombia. So here, the unit commitment is hourly. Hourly, we have an amount of energy that we have to deliver. And if you can see, there is a lot of hydro that is in the blue color, that is in the base of the dispatch. This is because in normal condition, and when I'm talking about normal condition in Colombia, is when we have normal hydrology, or the hydrology is above or in the average of the inflow, of the historic inflow. So in normal condition, we're going to see a lot of hydropower plants in the unit commitment. And we can see in yellow the natural gas plants that always have an important role in our system. Like, for example, a combined cycle unit that TEBSA has. Okay, I'm talking more about thermal power plants. In this slide, I'm talking about the basic frame of a thermal power plant. I mean, thermal power plants have in config like a minimum up and down time. And when I'm talking about minimum up and down time, is the minimum hours in our case. Minimum I'm talking Colombia case. Minimum up and down hours that the plant needs to be offline or online to operate and avoid damage or thermal fatigue. A startup ramp is another constraint. In Colombia, we have a kind of rules to follow, and in those rules, we can report or we can accept a model or another model. I'm going to explain more about that. But in the startup ramp, model 1, we can have 3 kinds of startup ramps: hot, warm, or cold ramp, the startup ramp. So each generator thermal power plant has to declare energy blocks for this startup ramp. And also for the model 1, that is the startup ramp, has to declare a shutdown ramp in blocks, in hourly energy blocks. And there is another ramp, there is the up-down ramp, that could be model 2 or 3. The model 2 I'm going to explain in the next slide, but the model 3 is a linear approximation about the down and down, up and down ramp. There is additional fires, and it's actually a conception for each plant. Okay, and I'm going to stay here in this slide because it's the most important slide of the presentation, because here we will explain the work that we have developed in this research. So for TEBSA, combined cycle plant, we need at least 2 gas turbines to start 1 steam turbine. That's a rule for us, for our plant. So the developer of this plant, the developer recommendations to avoid equipment failures like blade erosion, as I showed you in the picture before, in the steam turbine. Because just with one gas turbine, the plant can get the steam in the correct temperature and pressure to operate the steam turbine. So to get the steam in the correct thermal conditions, we need at least two gas turbines online, two startups, and a steam turbine. I think, okay, here we can see in the graph that, for example, we start here the first gas turbine, and then we start the second gas turbine, and then two gas turbine online. The second constraint describes how many hours you need to warm up the gas turbine. State of the gas turbine. That is very important. For example, if the gas turbine has more than 8 hours offline, the startup of the steam turbine is going to be they need to be startup at least 8 hours to produce the steam needed for the steam turbine to generate the quality of the steam that we need to produce energy with the steam turbine. The third constraint is steam turbine. As I told you now, they also have different types of startups. So they can have a cold or hot startup. And the last constraint is a very interesting operational constraint because it refers to the equal load distribution between the gas turbines to avoid delta temperatures between the surface and the center of the rotor of the steam turbine. In other words, if the gas turbine has different power outputs, each gas turbine will generate steam with different thermal conditions, and it will result in different temperatures in the rotor of the steam turbine. Okay, the problem description. Right now, the Columbia ISO doesn't have a correct model to simulate the combined cycle unit here in Colombia, in our system. So today, the ISO simulates TEBSA combined cycle gas turbine in an exact model that has a visual basic macro. This model doesn't have the most important combined cycle gas turbine operational constraint that I mentioned before. So this could end in equipment failures or thermomechanical fatigue. The combined cycle gas turbine plant couldn't meet the unit commitment plan because the Excel model output will be far of the current output that the plant can give. So it will result in deviation of the unit commitment plan and also in penalty. So right now we have an Excel model like this that is not the correct way to represent or simulate our plant. Technical constraints are not represented, so we have a problem right now. So what we did is to develop this model, and I'm going to try to explain this mathematical problem of simulation in a simple way. I'm not going to focus on the mathematical equation, but I'm going to try to explain about the optimization model that we developed. Okay, but first of all, this model is an optimization model, and it's a mixed integer problem, it's a MIP problem, because the unit commitment variable should be 1 or 0. In other words, the turbines are on or off. Okay, and first talking about the objective function of the optimization model, the objective function aims to minimize the total cost of the fuel used to produce energy, and to minimize the startup of each unit, because you need fuel to start up a unit. For each unit of the combined cycle, you need fuel. Also, they are penalized in the not served energy, the waste of steam, because as I told, with the gas turbine, you produce steam, you generate steam. But if that thing is 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 not used to produce a generation with a steam turbine, you are wasting steam. You are not taking advantage of the efficiency of this kind of technology. And we penalize also the imbalance load between the gas turbine to avoid the delta temperatures in the steam turbine. Okay, I'm going to talk more about the constraints of the problem. The first group of the first set of constraints talk about the energy balance constraint. The energy balance constraint represents is one of the most important inputs of the model because it describes all the energy dispatch that we want to simulate. So here, the input is L, or the load, and the output is the GCCT variable. These variables are the non-served energy, and E is a slack variable. The second set of constraints are related to the operational limit for both gas and steam units. This operational limit constraint guarantees the minimum and the maximum output of the unit. And finally, the third set of constraints describe the combined cycle constraints. This set of constraints guarantee the coupled operation between the gas and steam turbine if there are at least the minimum number of gas turbines required to operate a steam turbine. So, for example, in this equation, this constant NUG is the minimum number of gas turbines that we need to operate one steam turbine. In this part of this equation, we are describing when the steam turbines are doing a hot or cold startup, depending on the thermal state of the gas turbine. I'm going to talk more about this part in the next slide. Okay. In this slide, I'm going to talk about the constraint related to the combined cycle operation and the minimum up and down time constraint. So in this set of constraints, this set of constraints describe the relation between the gas and the steam turbine. This means how many energy can be produced by the steam turbine for each megawatt produced by the gas turbine. In our model, this relationship is represented by a steam factor equal to 0.613. In other words, for each megawatt that you produce with the gas turbine, you're going to produce 0.6 megawatts with the steam turbine. There is another constraint here related to the unit commitment constraint. As I told you, the minimum up and down time constraint for the unit, represented here below in the slide. Okay, this set of constraints describe the model 1 and 2 related to the ramp constraints that I mentioned before. There are 2 times of startup, and depending on the thermal state of the whole plant. It's cold, warm, off, and hot startup. And there is only 1 type of shutdown ramp in all the energy blocks. So this set of constraints represent or describe that startup or shutdown ramp. In this slide, I describe the constraint related to the operational constraints, like the type of a startup of the steam turbine, depending on the gas turbine, and the load distribution between gas turbines to guarantee the input temperature in the steam using the steam turbine, used by the steam turbine. Perfect. So talking more about the study cases, these are the parameters of the combined cycle gas turbine plant. These are a hypothetical parameters. It's not real, but it's something that this parameter is close of the number that we have in our plants here in TEBSA in Colombia. So here we have, for example, The installed capacity of the combined cycle plant, for this example, is 800 megawatts. We have the minimum energy output, that is 210 megawatts. We also have, for example, the cost of the production cost, that for this example is $120 per megawatt. The cost of the non-surge energy is $500. The cost of the startup of each unit is $15,000, for example. The MGG factor, that is the minimum number of gas turbines that you need to start up one steam turbine, that is 2. The steam factor, the number of gas turbines, that is 5, and the steam turbine 2. So in this plant, we're going to have 7 units, 5 gas turbines and 2 steam turbines. Also, we have here the parameter related to the combustion turbine and the steam turbine. Each combustion turbine has a start capacity of 100 megawatts, has a minimum output of 16 megawatts, and also the steam turbine has a maximum capacity of 170 megawatts and 80 minimum output of 80 megawatts. And this is very important. When the steam turbine is going to make a hot startup, it has to make a ramp of 80 megawatts. And when the ramp, or the startup ramp, is a cold ramp, a startup, it's going to make and going to produce 30 in the first hour, 30 megawatts. These are the hot, warm, cold ramps. I mean, the energy blocks that they have to do to meet the minimum output of the plant, and the shutdown ramp. So in this first case, imagine that 3 of the 7 units were on at the beginning of the day, and the dispatch that we want to simulate is in the black line, or the load here. So which is I mean, this dispatch that we want to simulate is to shut down the whole combined cycle at hour 5, and then put into the maximum capacity at hours 2 from 22. So this is the line, the black line is the dispatch that we want to simulate, is the input. The red line is the output of our model. And the yellow line is the output of the heuristic model that we have right now, the Exxon model. So we can see that our model dictates a smooth shutdown compared to the yellow or the heuristic model. So we see that the red line is above the yellow line. That means that our shutdown, or the shutdown of our model, is smooth. It's a smooth shutdown. And then the model decides to make a hot startup at hour 15. So we can see that the startup is a hot startup and start in this hour 15. We can see also here very interesting information in this graph in the right side of the slide. For example, we can see that the steam turbine number 1 make a hot startup, and the steam turbine number 2 makes a cold startup. And they can be a startup only if we have at least 2 gas turbines online. That is what we can see, and we can make sure that our model is making or is taking into account this constraint very faithful. And in this other example, the combined cycle unit plants are offline at the beginning of the day, and we want to put the plant in the maximum capacity from hour 22 to hour 22. But what is important here, what is very important here, is that our model dictates a warm startup. It's not a hot startup, like, for example, the heuristic or the Exxon model here. But if you can see, the heuristic model or the Exxon model that we have right now make a hot startup, and it's not true, because we and as you can see, the condition or the thermal state of the plant is cold. They are cold or warm. So you have to make a warm startup to make sure that all the constraints or all the equipment of the plant will not fail or will not be suffer thermal mechanical fatigue. Also, we can see here at the right of the slide that the steam turbine makes cold startup. 30 for the first energy output at 18 hours for the steam turbine number 2 is 30, and also the output and the first output energy for in the first hour of the steam turbine number 1 is 30. So that means that the plant or our model is making the coverage of the right decision. Okay, the conclusion and the recommendation. Well, we propose uh, an original formulation for individual gas and steam turbine units to guarantee the specific characteristics of the steam that we need to operate steam turbines. The correct representation of the characteristics is necessary to minimize the impact of the thermomechanical factors produced by the energy output. That is very important. And this is very important that the ISO take these constraints into account in the unit commitment model. It also has to increase the useful time of the combined cycle unit and the reliability of the combined cycle, minimizing the future failures. We propose a level operation constraint to allow for an even low distribution among the individual gas turbines to avoid the delta temperatures in the steam rotors. And our work improves upon the risk model that we have right now. Future work, of course, we love that the ISOs can represent or use this model into the unit commitment problem to improve the solution of the dispatch that they do right now. And of course, to take into account the important role that the combined cycle gas turbine have in our system. And of course, we expect that this work can be used for work in other ISOs and other markets around the world. Okay, thank you very much for your attention. Thank you, everyone. Thank you, Judah.
All right, everyone. At this point, we'll move on to questions and answers. If you have any questions for the speaker, go ahead and ask them. You can either put them in the chat or just go ahead and unmute yourself and ask. Thank you.
Thank you for your nice presentation. This is Farnos from Texas A&M. And my question is that how do you think it's possible to change from a self-unit commitment to a general unit commitment? Is it possible to extend this model to the whole grid?
Yes, of course. How it could be possible? Thank you, Farna, for the question. It could be possible because we developed this mathematical model thinking on that we can migrate this equation easily to the unit commitment problem because all the equations that you're going to see in a general unit commitment problem are represented here in our model. So what we need to do is just to put in the ISO unit commitment model the operational constraints that we have here, the combined cycle unit constraints related with that represent the relationship with the gas turbine energy and the steam turbine. Put it that we put here in our model, put into the general unit commitment model, and I think that it could be easy to implement. So we hope that the Colombia ISO can do that easily, and of course, I think that these are general constraints for all combined cycle plants in the world. So maybe we can use these rules or equations or models, optimization models, to take advantage of this in all the general unit commitment programs in all the ISOs that we have around the world.
I have a question for you, Mauro.
Oh yeah, sure.
Yeah, given that your plant is operating more than likely in very hot and humid conditions, I'm guessing, being near the Caribbean coast, do you have to worry or do you have to consider a lot about the conditions of the intake air for the gas turbine in terms of the power that it produces as a result of the temperature difference or density of the intake air, or is that something that is kind of external to your model or not part of your model?
Well, that is not part of our model, but I think that is an interesting question because here in Colombia, in our plant, in our combined cycle plant here, we use okay, the 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 plant is next to a river, so we use the water of the river to make like a cooling in the equipment that we use to produce energy. So to avoid mm, like to avoid over temperatures that can damage the equipment, that can make thermomechanical fatigue, we use water to do that. But the problem is when we have the dry season, we cannot use the water anymore because the level of the river is very low. So that is a difficult problem. It's very difficult for us when we have this kind of problem. And what we try to do is to not to use the water of the river, but also bring water from other body water near or close to our plant. It's not it's not part of our model, but it's a good question because we passed through that kind of problem before.
Thank you.
So how can you extend this model when you have uncertainty represented? Specifically, if you're going to have the representation of renewable resources, what kind of changes do you have to make to your model to be able to be integrated into a full-powered unit commitment?
Hi, George. That's a fantastic question. We think
So that and
that
75 cents will get me some Colombian coffee if Juan Valdez is around.
okay, okay, sure, sure. We can, George, thank you very much. Well, George, your question is very, 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 very good because we talk about that question, about that situation, and with Sonia, that is my coworker here in this work, uh, we use the same unit, self-unit commitment problem in a hypothetical system with variable energy resources like solar and wind. And what we saw is that we don't have to change anything because the uncertainty is just in the variable energy resource, in the in the solar, wind, and hydropower generation. With thermal power generation, uh, we don't have problem because we have the fuel. The fuel is there. So what we have to care about is that the operational constraints have the good representation as we did in this model. And when I'm talking about a very good representation of the operational constraints, I'm talking about the ramp, the startup ramp, the up and down ramp, the minimum down, up and down time constraints, the operational constraints that represent the relationship between the steam and the gas turbine energy production. So We don't have to change anything of this model. We did the homework. We did the homework. We take this model and we put it into a small system with variable energy resources, and it works perfectly.
Thank you.
Oh, you're welcome. No problem.
Really appreciate those questions.
I'm gonna send you with Judah with Joseph the coffee, the Juan Valdez coffee.
Okay.
Yeah, I actually that would actually be logistically possible because I actually used to live in Champaign, which I think Dr. Gross, I'm sorry, is based at University of Illinois. I used to live in Champaign, so and I'm actually just up the road in the Quad Cities, so I'm less than 3 hours away, or around 3 hours away. Yeah. And my next question actually was, how long does it take to solve this model?
Well, seconds. I mean,
So, okay.
for one unit commitment problem of 24 hours, it could take like seconds, 30, at maximum 1 minute. Maximum 1 minute. It's not that big. Of course, it depends in the software, simulation software that you're using. We are using here, and I didn't mention, I'm sorry about that. We are using here Ciplex. So Ciplex is a really good optimization software, a really good tool that solves this kind of problem very quickly. And of course, it depends in the computer description that you need to solve this problem, and it depends also in the software of the tools that you are using to solve the problem. But here we use a standard laptop. My laptop is an Intel Core i7, 8th generation, with 8 GB of RAM, and it runs in 1 minute maximum.
This is for a day, yeah, Mauro, for a 24 hours solution unit commitment, yeah. Okay.
Yeah, 24-hour unit commitment. Yeah.
Well, that's good because it would seem therefore that if you could do that on a laptop, then the barrier for entry for using this for a utility is pretty low. Like they don't have to, have access to a data center or a server farm to actually run this model.
Yeah. Now, if we integrate this model with the ISO unit commitment, that of course is bigger. I mean, it's a big problem. I think that it would take more time to solve the problem, and maybe more than 1 minute, 5 minutes, or maybe, I don't know, 10 minutes, but it depends on the computer that you are using and then solver that you are using to get the solution. The most common software that we use to solve this optimization problem are Ciplex and Gurobi, that are the most common solvers around the world to solve this kind of problem.
Would you see any utility in adding a machine learning component to this too? Or would that be something that's not particularly applicable in your case?
Well, that's another fantastic question. Because we have another problem here related with the failures of the unit. And when I'm talking with the failures, is when, for example, during the operation, the gas turbine can break down. We have to take off that turbine because something that we didn't expect it. So to solve or to anticipate to that kind of error, we can use machine learning. And here in TEBSA, we are working in that field very hard. We are developing like artificial intelligence models, machine learning models, to anticipate to that kind of event, to forecast or to anticipate when we could have an event on in what kind of condition with a unit gas turbine or a steam turbine can fail. And for example, it depends on the temperature, the practice, the very conditions, many kinds of conditions. And we thought that maybe we can integrate machine learning with optimization models to simulate this kind of cases, to anticipate this kind of failure that we can have during the operation. So what we get with that, it helps us to do a good maintenance plan to avoid that kind of problem in the future.
Excellent. I know everybody is kind of constrained for time. I think we have time for one more question, if anyone's interested. We're just bumping up on the forecasted end time for this meeting at 7 p.m.
Nobody else has any questions? I just want to point out, I think the beauty of the Mauro's study and research with Sonja is, usually here in the US, this kind of plants, like coal plants, nuclear plants and combined cycle plants, has been used for base load power plant, as a base load power plants, serving all the time. You just, due to the fact that they cannot change their power output quickly, they have been used all the time as a base load. You turn on the generator is online, and you keep it there, for a few days before actually you think about it to turning off or shut down these plants. With the introduction, as Mauro has mentioned, introduction of the renewable generation, and that you see as most a lot of high penetration of this generation for sure. There is going to be a need for this all of these combined cycle plants, for example, in this case, to adapt, to now to be able to vary, to change their output. So this kind of mathematical models and basically there is reflecting all of these physical constraints will help with definitely will help with the modeling these plants and how the ISOs are going to schedule these plants in the near future. Again, this has not been a problem so far here because of the way that this plant has been scheduled and used, but for sure it's going to happen and it's going to happen soon. So I think that is the remark, and the message here for Mauro's research, and it's really interesting work. Congratulations, Mauro, and thank you so much for joining us and sharing all of this knowledge with all this the group here.
Thank you very much, Jose. And I totally agree with you. Combined cycle unit is gonna be a good complement for the renewable energy. I think that Europe is passing through something like that right now, into a big energy crisis because they don't have enough renewable energy. They need natural gas to complement the variety of the intermittent of the renewable energy. So this type of model can help to save this kind of plants. I thank you again, Judah and Jose, for this opportunity to share this knowledge with you. I think that there is a lot of work in the future that have to be done, and of course, feel free to contact me if you have another question about this topic. It will be a pleasure for us to talk with you about this topic again.
All right. Thank you very much, Mauro, for presenting, and for everyone for your questions and for attending. We really appreciate it, and we look forward to having it at future events. I probably should have put it in my introductory slides, but we will be having an engineering ethics presentation that will be offering professional development hours and CEUs, and that will be early next month. We've already put the event out. I believe it's either November 5 or November 6. But you will see it on our Facebook page, and you'll also see it on the IEEE R4 Facebook page soon. I just need to get around to posting that. But I know someone was asking for PDH. We are definitely aware that that is a need of many of our attendees, and so for future tech talks, we'll try to have PDH also. We've had a bit of a transition in our section where we have new people who are putting these meetings together, and so those people are still getting used to the process of applying for and getting PDH for our attendees. So thank you very much, everyone, for attending. Take care and have a good evening, and thank you very much, Mauro, for presenting.
Thank you for having me here. Bye bye, everyone.
All right.
Good night.
Take care. Bye bye.